x in between A and B. We'll say right here. Okay. And suppose that I wanted to find the area underneath the curve between A and x. Okay. Well, then we could write this as that area. Actually, no, I don't want to do that. We could write that area as the integral from A to x. And I'm going to use f of t dt. You'll see why in a second. Way back when we first talked about integration, we said it doesn't really matter what variable you use. I don't want to use x because x is a point. In fact, this is a function f of x. So I want to be really careful. Variable doesn't matter, so I'm going to use t. We'll see why a little bit later. So bear with me. Yeah, we need to use some function other than f of x. Okay. Notice that where I chose x is not important. So this integral would change depending on where I put x. If I put x kind of, over here, the integral would change. If I put it over here, the integral would change. So really, this integral varies. In fact, we could even say that this thing is actually a function. We could say that we could call it f, the function capital F. Okay, so be careful with lowercase and capital S. But we can call this integral a function because it varies, it changes. Okay, any questions so far on notation or anything I've said until now? In fact, we could even write big F of x. That's fine. Okay. So then the question is, what does f prime of x, big F prime of x, what does that represent? If the integral is the area, and that's represented by f, this was an exploration, and you're supposed to discover all of this stuff, and I decided that that was probably a bad idea. So, f prime of x is the change in the area. Okay, so f prime of x is the change in the area, or the rate of change in the area. So this is the rate of change of the area. Okay, f prime of x is the rate of change of the area. Okay, since f represents the area. Any questions on why that represents the rate of change of the area? So let's suppose that I wanted to change x a little bit, because we said x doesn't really matter. Suppose I wanted to change it, and I just wanted to add on one kind of small rectangle here. Go the other way. Purple for your learning convenience. Suppose I wanted to add on a little bit more. Okay? We would call this delta x, right? That's the change in x. And this purple area, we would call delta F, because that's the change in the area. Delta F is the change in the area. Okay, important distinction here. Delta F is the change in the area. F prime of x is the rate of change of the area. Okay, so don't get those two confused. But this is the actual physical change in the area. If I want to know how fast it's changing, so if I want to know how fast the area is changing, I take delta F, whatever I've changed in F, divide it by delta X, and let delta X approach 0. if I want to know how fast that area is changing, if I want to know the derivative of big F, then I'm going to try and take delta x and shrink it to 0. If I take delta F divided by that, that'll give me how fast the area is changing. Notice if I shrink this really, think about it as shrinking it infinitely small. Okay, so the book did not do this in the solution manual or anywhere, but I think it's helpful if we think about this extra area that we've added in this sense. If I want to know what the actual change in F is, the change in F area, then here's what I'm going to do. I'm going to treat it kind of like a triangle. It's going to be the width of the triangle, which is delta x, times whatever the function height is. Remember, that was precisely true if this was a perfect triangle, but it's got a curve here at the end, so kind of, since we're amongst friends, that's what we'll say for now. We'll say it's delta x, which is the horizontal distance, times f of x. Okay.
Triangle.
Notice, if we took and divided both sides by delta x, we could then say, hey, the function f of x, the original, y equals f of x, that function is given by delta f divided by big F. It's worse. Delta f divided by delta x. With the important caveat that that is only true. The function value is that so long as we shrink this rectangle down to infinitely close to 0. Notice if I shrunk this down to 0, I'm really looking for the rate of change of the function. The rate of change of the function will be the rate of change of the area. What will be there in a second. So let's add this. Limit as x approaches, as delta x approaches 0. Okay. So we've got to shrink this distance down to 0, and then that becomes true. Okay. Because of this, we can say this. Then, f prime of x, big F prime, change in the area, equals the limit as delta x approaches 0 of change in f divided by change in x. Okay, because remember we said, hey, this kind of represents the area, but it only represents the area, or the rate of change of the area, if we take delta x down to 0. Okay, so rate of change of the area we already established earlier was f prime of x. I'm just saying, hey, f prime of x equals that mess, and we just said that the mess is the same as f of x. Okay. So, what does this mean? All right. So we might say, who cares? Okay. Means this: f prime of x. That's the same as d dx, derivative with respect to x, of f of x. Remember way back at the beginning, we established f of x was this integral. Big F of x was the area under the curve. Okay, so if I want to take the derivative of big F of x, I'm actually taking the derivative of this integral. So the integral from a to x of f of t dt. Alright, well,
What's the significance of the dx?
all I did was change notation. I went from f prime of x and changed the notation to d dx of x. That's helpful because now I can make the substitution. I can substitute f of x, this integral in for f of x. Alright. Now, we just established up here that f prime of x equals f of x. So in other words, the derivative of the integral is a function. In other words, if I wanted to start at the function and end up back at the integral, I would take the antiderivative, or the opposite of the derivative. If I wanted to go the other way, start from the integral and go to the function, whatever it is, I can take the derivative of the integral, out of the function that's inside, not of f of t, but of the integral. So this is how Newton and Leibniz finally related integral calculus to differential calculus. They said, hey, let the integral be a function that varies. Let's do some analysis on what the rate of change of that area is. And then they said, hey, well, if we, now this, like I said, they didn't make this assumption, I think it's helpful though. We say the area is a horizontal distance times the height. So long as we let that horizontal distance approach 0, then that's the same as the rate of change of the area, and then we end up with the derivative of the integral is the function. It's something that you probably all kind of assume, but I think there's value in kind of seeing why. So if that was mind-blowing, and it probably was, it's on video. Are there any questions? I know this is kind of heavy conceptual stuff, but are there any questions